Hello, let's start. You have notebook open and a pencil ready. Make sure you pause and think and take notes. Try to answer questions before you hear the answers. Let's go. So last year you learned about sine, cosine, and tangent and ratios in a right triangle. In other words, they only made sense for an acute angle. This year we already generalized sine and cosine functions from an acute angle to any number, any angle, and also any real number if you're thinking about radians. But what about tangent? Today we are going to generalize that tangent function also from acute angle to any angle, well, almost any angle. Let's consider a right triangle in a unit circle. In this triangle, we are going to look at the angle theta in standard position. So tangent theta, as we know, is the ratio of opposite leg over adjacent leg, which in this case will be equal to BC over OC. Again, opposite leg over adjacent leg. But as we know, in a unit circle, BC also serves as the vertical coordinate of point B, which is equal to the sine theta. OC is the horizontal coordinate of point B, which is the cosine theta. So what we just showed is that tangent theta, for acute angle at least, equals to sine theta over cosine theta. This is a super important equation, and we can treat it as a definition of tangent actually. Let's look again why this makes sense. We know that tangent theta for this triangle will be opposite leg, which is A, over adjacent leg, which is B. We know that sine theta in this case will be opposite leg A over hypotenuse C, and cosine theta equals adjacent leg B over hypotenuse C. So if we are going to divide sine theta by cosine theta, we will have to divide A over C by B over C, which means we have to multiply A over C times the reciprocal. So C cancels, and we end up with A over B, which is tangent. So there's nothing surprising here, really. But now we are going to see how tangent behaves in other quadrants in a unit circle. And also it would be really nice to see a tangent as a segment, because it really helps to visualize sine as a vertical component and cosine as a horizontal component of the triangle. That's what we're going to do next. Have you ever thought about the word tangent? Why this word is used for tangent ratio? From geometry, you remember the tangent line is a line that touches a circle in a single point. But so far we haven't seen anything about tangent ratio, which is touching, but we will see it in a moment. Let's consider an acute angle theta in standard position, and let's look at the triangle OCB. As we know, tangent of an acute angle is opposite leg, which is BC, over adjacent leg OC. But I hope you notice that line that is drawn here, the line DE. This is the line which I drew perpendicular to the x-axis, and it forms another triangle here, OED. So let's compare these two triangles. Triangle OBC and triangle OED. I hope you remember from geometry that these triangles are similar. Why? They have common angle theta, and both of them have right angles, angle C and D. And two angles are enough to state that two triangles are similar. Because they're similar, we can state equal ratios. BC over OC, short leg over long leg in a small triangle equals short leg ED over OD in a large triangle. BC over OC, as we know, is tangent theta. Let's see what we know about ED. Nothing. So this is just ED. What do we know about OD? OD is the radius of our circle, which is just 1. So we just proved that ED segment equals to tangent theta. So we just proved that this segment ED actually equals to tangent of angle theta. So it turns out that this line is not just a tangent line to our circle. Actually, it's called the tangent line, and that's the line where all tangents live. Let's look at one more angle to better understand this idea. Let's say we consider another angle. Let's call it angle alpha. When it intersects with the unit circle, that's the point that has coordinates x coordinate cosine and y coordinate sine. But this triangle is also similar to this big triangle, and if you consider the ratio of sine over cosine, which is tangent, and it will be equal to this segment over this segment, which is 1. So in any case, we are going to get that tangent of angle alpha equals to, let's call it F, segment FD. So this segment, this length. By the way, when you look at this picture, you can estimate roughly, because this is a unit circle, and this length is 1, this will be a little more than 1, maybe 1.2, 1.3. And what will happen when the angle increases? This tangent value is even larger. This one is even more than 2 probably. And we can make it as large as we want as angle increases and gets closer and closer to 90 degrees. So what happens with tangent 90 degrees? According to a diagram, it makes no sense because the vertical y-axis will never intersect with the vertical tangent line. But also let's think, the tangent is, as we define, sine over cosine, and cosine 90, as we know, is 0. So we would get 1 over 0, which does not exist. Let's see what happens in the second quadrant. Let's look at some angle in the second quadrant, and if you extend it, it doesn't intersect our line. So what are we going to do? Think. So hopefully after pausing and some thinking, you guessed that we can extend this line in the opposite direction. So wherever this line intersects our tangent line, that will be called tangent, let's call this angle beta, for example, tangent beta. As you can see, this tangent will be negative. And it makes sense because we divide sine beta over cosine beta, and sine, as we know, in the second quadrant is positive, and cosine in the second quadrant is negative. So the tangent will be negative as well. As we keep going around the circle, let's say if you go to the third quadrant, the angle here will actually have the same exactly tangent as our original angle theta in the first quadrant. Why is that? Sine and cosine, both sine and cosine for these two angles are opposite. So if you divide sine by cosine positive values and sine by cosine negative values, you're going to get the same tangent value, which is this number. Okay, let's start graphing tangent function. Tangent 0 crosses the tangent line at 0. So the value is 0. We can plot our first point. Okay, let's look at 45-degree angle. 45-degree hits the tangent line at the height 1, because this is 45, 45, 90 triangle. The radius is 1, so this must be the same leg. So tangent 45-degree is 1, and we can plot our second point, pi over 4. Oops, we need the vertical axis here. Scaling 1, 2, 3. Okay, so this is our second point. Now, let's see what happens as our angle keeps going and approaching to 90 degree. As we know, tangent keeps increasing and increasing and increasing. Take your calculator and estimate with a calculator tangent 80 degrees. It will be big, maybe 5, 6 units. If you keep going, tangent 89 degrees will be even bigger, and tangent 89.9 degrees, maybe even more than 100. So our values will increase, but tangent 90, as we already know, doesn't exist. In order to show this on a graph, we are drawing a vertical line, which is called, how? You've seen that before? Yes, it's called the asymptote, and the purpose is to show that the graph will approach this line but never touch it, because as x is approaching to pi over 2, as our angle is approaching pi over 2, the y is increasing without bound, but the graph never crosses this asymptote. Okay, now let's look at this area. What happens as our angle goes from 0 to negative pi over 2? Tangent values are negative here, as we know. Let's look at negative 45 degrees. Tangent negative 45 degrees, guess, is negative 1. And as we keep going away from the 0, but approaching to negative pi over 2, our y values remain negative, and tangent values increase without bound, just in a negative direction. So for negative pi over 4, once again, we have negative 1 value of tangent, but as we keep moving, our y values become increasingly big and negative, and we need to draw our new asymptote at negative pi over 2, which is our virtual boundary. And that's how the graph looks like. Once again, just trace how the graph goes from negative 2 to positive, from negative pi over 2 to positive pi over 2, from this angle to this angle, starting down below and then going up and reaching 0, and then going up, positive and infinite on the graph. Now let's see what happens in this interval between pi over 2 and pi. In other words, when the graph goes from pi over 2 to pi in the second quadrant. Exactly at pi over 2, there is no value of tangent. It's huge and positive. But the moment your angle crosses from first quadrant to second quadrant, tangent values become negative. As we rotate counterclockwise, our tangent value change from big negative to smaller negative. And as we approach the pi angle, 180 degree angle, they become smaller. For pi, tangent is actually 0 again. So tangent pi is 0. Tangent of an angle which is a little more than pi over 2 is huge negative. But as we get closer to pi, tangent values get smaller, and the pattern repeats. As we go to the third quadrant, the tangent values become positive again. and they grow from small positive numbers to big positive numbers. So our curve keeps going, and when we get to 3 pi over 2, we need to draw the asymptote again, because at 3 pi over 2, once again, tangent doesn't exist. And the pattern continues at 2 pi, tangent is 0 again. In fact, around 2 pi, the same pattern continues as around 0, because this is just a new cycle, and we can go on and on and on. At this point, I would say you should really graph y equals tangent x on your graphing calculator. Do it in degrees and do it in radians. Both time, look carefully, trace, look at the tick marks. And we will continue tomorrow. If you feel that you were confused at some point during this video, you really should watch it again. Good luck.